You ever wonder why magnets stick to your fridge? I mean, really wonder? You think it's a simple question, but the real answer? Well, it takes you down one of the deepest, weirdest rabbit holes in all of physics. So let's just dive right in and see what's really going on. And look, this wasn't just a puzzle for you and me. It famously puzzled the legendary physicist Richard Feynman. Not because he didn't know the answer. No, it's because he knew there wasn't a simple, satisfying one. He saw it for what it truly was, a really profound question hiding in plain sight. So let's get right to it. What is the real reason magnets attract and repel each other? Let's find out. This really gets to the heart of the problem. Our brains, we crave a simple mechanical story. We want to imagine tiny gears turning or little hooks grabbing onto each other. But that's the whole point Feynman was making. For the fundamental forces of nature, that kind of story just doesn't exist. Reality is playing a completely different game. The real answer starts right here, with one of the four fundamental forces of the universe, electromagnetism. So forget the gears and hooks. This is a basic property of how our universe is actually put together. Now, to get this force, we have to look at the electron. There's this super common picture we all have in our heads of electrons as these tiny little planets spinning on an axis. It's a nice visual, for sure, but it's just plain wrong. In the quantum world, spin isn't a motion. It's a fundamental, built-in property, just like an electron's charge or its mass. And here's the crucial part. Because of this quantum property called spin, every single electron acts like a tiny built-in magnet. It has something called a magnetic moment. It's not something it does, it's something it is. It just comes with the package of being an electron. So how do we get from one tiny electron to a magnet you can actually hold? Well, in most materials, all those little electron magnets are pointing in totally random directions, so they all just cancel each other out. But in special materials, like iron, what we call ferromagnetic materials, something amazing happens. You can get their electron spins to all line up in the same direction. And when billions upon billions of them do this, their tiny magnetic fields add up to create one big, powerful magnetic field that we can actually feel. So why the push and the pull? It's all about energy. Everything in the universe wants to be lazy. It wants to settle into the lowest, most stable energy state possible. When you bring two magnets together, their fields interact. If opposite poles are facing each other, the fields align in a way that creates a lower energy state, so boom, they attract. If the same poles are facing, the fields fight each other, creating a higher, unstable energy state, so they push apart to get away from it. And this isn't just for magnets. This is a core rule of the entire universe. A ball rolling downhill, a hot cup of coffee cooling off. Nature is always, always trying to find the lowest energy state it can. The push and pull of magnets is just nature doing its thing. But here's where we slam right into the Feynman wall. We've explained how it works, right? Quantum spin, fields lining up, energy states, but we still haven't really answered why. And this is Feynman's brilliant and maybe a little frustrating insight. Science is a master at explaining how, but the question why eventually leads to a dead end. Let's just follow this train of thought for a second. You ask, why do magnets attract? And I'd tell you, because their opposite fields align to lower the system's total energy. Sounds like a pretty good answer, right? But it just begs the next question, which is, okay, but why do the fields have a lower energy when they align? And the answer to that is, well, because that's what the mathematical laws of electromagnetism say. Okay, but then you have to ask, why does the universe follow these specific laws and not some other set of rules? And right there, that's it. Physics has to just throw up its hands. There's nothing deeper to point to. And this is the absolute key to the whole thing. At the very bottom, we don't find a deeper cause, no little gears turning. We simply find a description of how reality is. The laws of electromagnetism don't have a reason behind them. They are the reason. Feynman used the perfect analogy for this. Asking why nature follows these physical laws is just like asking why 2 + 2 = 4. There's no deeper reason. It's a fundamental truth that we build everything else on top of. It just is. What's fascinating is that we don't seem to get this frustrated with other forces. I mean, think about gravity. It's a mysterious force that acts over huge distances with no visible connection. But we've lived with it our whole lives, so accept it. It feels normal. Magnetism only feels weirder because we can actually pick it up and play with it. And that makes us demand that simple, hands-on explanation that, by the way, doesn't exist for gravity either. So let's put it all together. The most honest, complete answer to why do magnets work is this. They work because our universe just happens to have this fundamental property called electromagnetism. And the quantum rules of that property say that electrons have a built-in magnetic field and that those fields can line up to create a force we can feel. That's the deal. And I want to be really clear about this. This isn't a cop-out. It isn't a failure of science. It's actually the opposite. It's a sign of incredible success. It means we have pushed our understanding all the way down to the bedrock of reality. We've found the edge of what why even means. And that just leaves us with this one last kind of mind-bending thought. That simple question about magnets, when you follow it all the way down, it stops being about physics. It becomes a question of philosophy. You're not really asking how magnets work anymore. You're asking, why is the universe itself built this way? And that might be the most interesting question of all.